Well, hello, NATR 346 water class, the brave souls of NATR 346 2020. This is, I think, will amount to about a 20-minute talk. And the purpose of this talk is just to introduce you to the basic concepts of precipitation. If you've had a course in physical geography, I highly recommend that. But if you have, then this will be old hat to you. You may have covered this in a high school earth science course, so I don't mean to introduce anything highly technical or esoteric here, but because precipitation is our ultimate source of water, I think it's important that we have at least a fundamental understanding of what causes precipitation to occur in the first place. So these bullets are what I'd like you to leave this lecture with, an understanding of basically how the atmosphere and air pressure systems work, states of water, the hydrologic cycle a little bit, and then this concept of relative humidity is big, and the adiabatic process is also important to understand, and then just what's a cloud and how does precipitation occur. So first we'll start with the concept of air pressure. And it simply is that the atmosphere consists of air molecules, and those air molecules are bouncing into each other at varying rates. And the hotter the air and more confined it is, then those air molecules will bounce against its container at a higher rate, and so that will give you higher pressure. Conversely, it's true if you cool the air down, those air molecules will be vibrating and bouncing off each other less, resulting in a lower pressure. And there's other reasons why in the atmospheric circulation system that an air might have high or low pressure. But it's a key concept because air will move from high pressure to low pressure. And we'll see that the reason we have a drought every year, and sometimes we have multi-year droughts in California, is because of high pressure systems that descend onto our state. And again, I told you this was fundamental, that the water it's actually, we take it for granted because we grow up observing condensation and evaporation and freezing, but it's very rare to have a substance on a planet that exists in all three phases in the normal temperature range. So that's a really big deal. And this is a nice diagram I like to introduce these topics. You can start at the top, and that's the most important part. Starting at the top when we have water vapor, it's important to note that water vapor at the top here is a gas. That's not a cloud. That's kind of an unfortunate drawing, I guess. Water vapor is not a cloud. You can't see water vapor. If you see it and it's a cloud, those are little droplets of water that are reflecting light. If it's water vapor, it's a gas just like nitrogen and carbon dioxide and all the other gases in our atmosphere. And so for us to get precipitation, the key thing is that we need to get from water vapor, and we need to condense that water vapor into water. All right, that's the focus of today's little talk. So here we are. We're very concerned about atmospheric moisture because precipitation is our ultimate source of water, and water vapor is the ultimate source of precipitation. So where does it come from, and how is it that it can turn from a vapor to a liquid for us? And here's where the concept of relative humidity comes in. So it turns out that warmer air can hold more water vapor than colder air. So if, let's say, you have a room full of air and there's a certain amount of water vapor in it, if you heat that room up, then that water vapor, in a sense, you can think of it has more room to hang out in the warmer air, and it will be very happy as a vapor. But if you decrease the temperature, like this blue arrow, then the relative humidity will increase, meaning the colder air cannot hold on to the vapor as well as warmer air. So one key method of getting water vapor to precipitate is to decrease the temperature of the air. And that will take that water vapor and make it essentially unhappy in its vapor state, and it kind of gets squeezed out of the warm air as you cool it down. So relative humidity decreases as the temperature increases. And the reverse is true. Relative humidity increases as the temperature decreases. And there's a certain point at which the temperature of the air decreases to the point where the water vapor no longer can hang out in its gas state, and that's a dew point, and it will turn into water there. When you get to 100% relative humidity, that is, there's no more room for water vapor in that air, then you will get condensation to occur. That's called the dew point temperature. So I like to zoom in on this idea of condensation, and something we experience all the time. If you have a cold glass of water, or maybe a beer, in my case, what happens, why, you might ask yourself in some detail, how is it that water forms on the outside of the glass? And most people say, yeah, that's condensation. Okay, that's cool. I kind of just want to explain that in a little more detail here. And that is, you let's start with cold water. That's water that has less heat energy than the surroundings. And so the heat energy that's in the glass will then move into the cold water, because heat energy will go from where there's more of it to where there's less of it. When the heat energy leaves the glass into the water, then the glass ends up being colder. Then you have a cold glass. Now think about the air right outside touching the glass. The heat energy in that air is then going to go in to warm up the glass. As a result, the air surrounding the glass will be colder. And then what happens when you take air with water vapor in it and you cool it down? Then you will get to 100% relative humidity, and that air right next to the glass will hit the dew point, and the water will condense out of the air and form on the glass. So something you see all the time, and you kind of, yeah, sure, condensation, that's cool. But that's exactly the same process that explains all of our rainfall, is that hitting that dew point and getting that condensation to occur. So the rest of this talk, or a lot of it, is really just in nature, in natural systems and rainfall patterns. How is it that air masses, warm air masses with water vapor, get cooled down to the point where they can condense? The other nifty thing about this is that there's a new company, I think AWD Technologies, that is attempting to just get a water supply by doing this condensation work in a big way. So they essentially have a very, very, very efficient refrigerator in effect. And certainly in a humid climate, they tested it out in Puerto Rico as a part of disaster relief to provide drinking water for folks by just taking this essentially efficient refrigerator and turning it on, getting the warm, moist air, the warm, high water vapor content air, and cooling it down and squeezing the water out of that air. And sure enough, these things were making drinking water for folks. So it's a very, and also, but Israel is pioneering work on maximizing the work that you can to get water vapor out of air for agriculture. We must get into this adiabatic process, because that is really, in natural systems, that is the main way that we get warm air to cool off and give us rain. So adiabatic just means heating or cooling that results from a change in the volume of the air. So you can imagine if you have a certain amount of gas molecules, and then you take that volume and you take that mass of air and you increase the volume that it occupies, then those air molecules are going to be bouncing around each other and hitting each other less, and the temperature decreases. And vice versa. If you take a certain amount of air and squeeze it in a smaller volume, then those air molecules are going to be bouncing off each other more, and the temperature increases. So there's a thing called this adiabatic lapse rate. Again, if you took geography, you would be all over this, but it's simply the rate at which the air temperature decreases as you go up in elevation. So why is it anyway that when you go up into the mountains, if you start in Sacramento, it may be 100 degrees, and then you go up to Lake Tahoe and it's 80 degrees? Why? Why is it that when you go up in an air balloon, the temperature decreases until it gets very cold in the upper atmosphere? And the reason is this adiabatic business. As you go up in elevation or up in altitude, there's less air pressure. And so those air molecules are banging against each other less frequently, and the temperature decreases. Hopefully that's a pretty intuitive concept. So the bottom line is that to get rain, you need to get the air to above 100% relative humidity. So you need to take air with water vapor and cool it down until it hits the dew point, and that vapor changes phases from a gas to a liquid. And then, with luck, it might condense into little droplets, and you have fog up in the sky called a cloud. But that doesn't mean you have precipitation. But we're just we're starting with the idea that we need to get that water vapor out of the air and condensed. So the best way to do that in a natural system is to shove that air up into air with less pressure and therefore colder. So there's 3 ways to do that: convectional, orographic, and frontal. Turns out for us, orographic is the big one, but we're going to cover all 3 because all 3 play a role. So convectional precipitation is just simply when you've heard of this urban heat island effect, perhaps. Solar radiation comes down onto the earth. It may heat agriculture field a certain amount, but if you've got materials that absorb that radiation and re-radiate it, then you're going to have warm air relative to the surroundings. The warm air will rise, and it'll rise. What happens when it rises? It's going to encounter cooler and cooler air. And then this line here, that's the dew point. Finally, this water vapor and this rising air gets to 100% relative humidity, and it condenses. It goes from a gas to a liquid. So that's convection. Here's another kind of cartoon for it. This is a classic cumulus pattern. If you're out and seeing the sky with a nice pattern of cumulus clouds with spaces in between, this is probably what's going on. Warm air is rising up to hit that condensation level or the dew point, and then it forms. A lot of times you'll notice when you look out at clouds, it looks like the bottom of the clouds are all at a flat surface. They all are at the same level, and that's because that is the level at the dew point level. That's the temperature at which the rising warm air hit its dew point. And you can definitely get significant rain from this pattern here. The other way to get warm, moist air up into higher altitudes and to its dew point is orographic lift, which is simply the air is shoved in with wind and it hits a mountain. How about the Coast Ranges or the Sierra Nevadas? So that air has nowhere to go except up. And as that is the mechanism to get the water vapor laden warm air up into higher altitudes, hit the dew point, and give us precipitation. And if you look at the Sierra Nevada and the rainfall rates, they literally start at very low, 10 to 20 inches, 30, 40, 50, 60, until you get to the top and you get much higher rainfall rates. It's all because of this orographic. The other implication of this is that as this moist air is shoving in, let's say from west and going east over the Sierras, on the other side of a mountain range like this, you're going to have what they call a rain shadow, because this air has gotten the water squeezed out of it. And so now it's cruising across here, but it doesn't have much water vapor. And not only that, there's a tendency for that air to come down the other side. That's the wrong way for precipitation. It's getting hotter and hotter, and the humidity is lower and lower, And so you're going to have really dry conditions on the other side. That's classic rain shadow. And here's just another kind of a sloppy diagram, but it's in the California, you'll see a little rain shadow on the east side of the Coast Ranges and a big rain shadow over there. Sorry, Nevada, we're taking all your water because we need it here in California. For one of the assignments, I suggest you can use this very map or a database to look up rainfall rates in California. This is just a general precipitation map for the state. You can squint your eyes and you can see the rain shadow effect here, for example. Here's moist air coming off the Pacific and hits the Coast Ranges, and then you've got dry conditions here. The big rain shadow is on the other side of the Sierra Nevada. So this red and these tans and these colors here mean not much rain. So you can see lots of rain in the Sierras, rain shadow on the other side. The other major way that you can get warm air lifted up is when one air mass clashes with another air mass in the cyclone. And this is what you'll see on the weather reports, these weather systems going through. I don't want to go into the physics of air circulations and how these things form, but suffice to say, it looks kind of like this. Sometimes you can get cold air close to the Earth moving along, and it encounters warm air, and this warm air has nowhere to go. It's kind of like the cold air acts like a mountain range, but it comes at you, and this causes the most violent thunderstorms and hailstorms. We don't see that very much. That's more kind of in a Midwest situation. But you can kind of maybe get the feel you've got really warm, moist air sitting there, very happy, and this cold air comes underneath and it violently lifts it up. If warm air encounters cold air and encroaches on the cold air, then that warm air will rise, but it's a little more gentle than when cold air invades. So now, that's just, again, I told you it was just the basics of how precipitation forms and occurs. The other variable for California is, why then do we have such variation in our rainfall? And how come we have a drought every year? It's called the Mediterranean climate. We have this Mediterranean climate, which is pretty unique. And it's tough for us because a lot of places, when they have a hot season, it's wet. It's hot and wet. And that's fine because, you can grow food when it's hot and wet. Our situation is when it's hot, it's dry. And so we have a really big drought and need for water during the summer. And then when it's cold, it's wet. Well, that's great. We get water, but it's cold, and so we don't need as much. So it's kind of upside down. So why do we have this? What causes that basic pattern of precipitation? The answer revolves around how the Earth receives solar radiation and how that changes over the seasons. Sorry, I went the wrong direction there. So, first concept, again, this is sort of the Earth Science 1 business here, but you can think that the Earth is a sphere. Radiation from the sun, we get a tiny, tiny fraction of it hitting the Earth, but it ends up powering our planet. And because it's shaped like a sphere, these arrows really tell a story. There are places on the Earth where the radiation from the sun hits the Earth directly and just hammers it with radiation. If you're up here, the radiation sort of just grazes past. For each little unit of radiation, it covers a wider swath of the planet than that same unit of radiation here, which just pelts a certain small area. And that is literally why the Earth is hotter at the equator than at the poles. It isn't because the equator is closer to the sun at all. It's just by virtue of this fact that the Earth is a sphere and the radiation concentrates just because of the geometry of it at the equator and spreads out and just glances more at the poles. So that's the driving force for atmospheric circulation patterns. So that's concept 1. Concept 2 is that the place where the radiation is most intense varies over the course of a year. In the wintertime, So I hope you can see this, a little blurry, but here's South America. And in the wintertime, the hot spot is down here, and we're way up here. So that's why our winters are cold. In the wintertime, we're getting more diffuse solar radiation input than south of the equator. In the summertime, see, we're up here in North America, we're getting hammered with that direct radiation input. So we're getting more solar radiation in the summer than we are in the winter, just because the Earth is tilted and it kind of leans in the summer, and then it kind of leans back in the winter. Ironically, in the summertime, the Earth is farther away from the sun than it is in the winter. So it's all about this tilt and where that radiation is hitting directly. That causes an annual cycle of weather patterns. So here's another diagram that just goes into that in more detail. In December, here we are up here in the northern part of the globe, and the direct rays are hitting the Tropic of Capricorn. They're hitting the southern part of the hemisphere of the globe. In the summertime, the direct rays are up north here, and that's again causes the hot season and our cold season. So lastly, and this is all going to tie together in the end, I hope, there are these generalized global circulation patterns. Again, this is classic geography. And in general terms, that radiation hitting the equator causes atmosphere to rise. And then you can get these global patterns. It rises, it heads north, and then it falls down. And as this air from the upper atmosphere is coming down onto the planet, it causes a high pressure. High pressure means that you're not going to get storms coming in because it's pushing away low pressure storm systems. And it also means that the air is getting warmer and higher pressure, and the relative humidity will then be going down, and your chance of precipitation goes lower. So in general terms, you'll get low pressures at the equator while the air is rising, and you'll get these high pressures at around 30 degrees latitude. That's, this is all very interesting up here at the poles as well, and the Coriolis force of these curves and all that. We're not going to get into that. Basically, where we experience our seasons here in California is because of this high pressure system and how it changes over the course of a year. So this is what it looks like in an actual map. The red line is that equator where the air is rising from being hammered by the radiation, and then it goes up, and then it comes down in these high pressure cells. And the most famous one is the Pacific High. And again, it dominates. So this is in July. This is our summertime pattern. We have high pressure all across the coast here. That high pressure prevents low pressure systems from coming in and giving us any weather, basically. Now, that's because of the way the Earth is tilted, and the fact that the equator effect, the direct radiation effect, is up here in the north. If we go and contrast this to wintertime, this red line then shifted down south. Again, because of the tilt of the Earth, the direct radiation is down south. You still have the basic circulation patterns. It goes up and it comes down, but the Pacific High now goes down to Mexico. So you're going to have to get your Pacific High in Mexico. And that allows this low pressure system to come creeping down and giving us these purple arrows that start coming in and hammering us with precipitation. Again, this is oversimplified, but I did want to give, hopefully, a helpful general picture of why are we hammered with a drought all summer, and then in the wintertime we start getting some weather. And this tilt of the Earth business and the radiation is really what's behind it all. Now I want to shift back into more classic sort of water resources terminology, and this is part of the watershed exercise and the concept of a watershed. So now that we have, let's say we finally got precipitation, we, we got the air, the warm water vapor air lifted up high enough to hit the dew point, condense into droplets, and fall from the sky. Here's another little by the way, that to get the water vapor, or I'm sorry, to get the water vapor to condense into water, it's helpful to have what's called a condensation nuclei, which is just a little particle, a teeny tiny speck of dust. So even that water vapor may be at 100% relative humidity, and it's not stable, it's not happy as a gas, it wants to be a water drop. It's encouraged to condense if there's a little bit, a speck of matter, a condensation nuclei. So each of these little raindrops theoretically has a little speck of something that allowed the vapor to condense around it, and that's where the concept of cloud seeding comes in. You can imagine that if there's air with vapor and maybe even fog droplets that is just wanting to drop but needs some more condensation nuclei, then you get up there in a plane and drop dust, in effect, certain kinds of particles, and it can encourage the vapor to condense more and get the droplets to condense more and finally get that water out of the sky and onto the ground. So sorry for that little diversion there. Okay, so here we are. The rain's falling out of the ground, and a fundamental concept in hydrology is a watershed. And a watershed is simply an area that is drained. So you could look at any river, and each river that you see has an associated watershed that feeds it. The other name for this that's interchangeable really is drainage area. So if you're standing here at this lake, you could ask, what area of the planet drains into this lake? And it has to do with topography and the divide. So for the homework, I picked out a particular watershed, and I'm asking you to look at this topography and find the divide and map out the watershed. It's a fairly simple concept, but it's important to understand because later in the semester we're going to be dealing with these watersheds and looking at the flow of water in these rivers that drain the watershed and predicting the flow in the river based on the land use. So it's all about, anyway, there's a great deal about range and management of these watersheds to protect the quality of the water in the river and in any lake that is drained. You can imagine it doesn't take much disturbance of the land in the watershed to cause erosion of soil, then sediment getting into the river. That sediment may have nutrients in it. The nutrients then go and cause algae to grow. The algae then grows and dies, and when it dies, it takes the oxygen out of the water. Lots of stuff can happen here. So the idea of a watershed for today and for this week is just know what it is. It's a drainage area that feeds a river or a lake. But then we're going to get into a lot about how watersheds are managed and what implication that has on water quality. And this is the last slide for the talk. And there's a homework assignment around this, just going to this data site. It's really pretty cool if you're into this kind of thing. But the big workhorse for California water supply is up here in Northern California. Because of the weather pattern in the Sierra Nevada, that Pacific High, when it migrates down south, it can park down here somewhere, leaving this area still not getting much rainfall. What happens though, that low pressure from the north comes down and it can really hammer this area with rain. California Department of Water Resources likes to keep track of these big 8 here and accumulate and add all the precipitation and track it over time, and they've been doing that for a long, long time. You can see this record goes back to at least 1923. So a couple of things about this chart. One, the hydrologic year goes from October 1st to September 30th. It's not a calendar year. And so we are here in late August. So I just printed this out today. And so you can see we're just about toward the end of the hydrologic year. And this greenish line is what they call an average year. This is taking every year they have on record and dividing it by the number of years. And usually these 8 stations will give us 51.8 inches of rain. This year, a little bit of a frowny face here. We're only at 31.9, and it doesn't look like we're going to have spectacular storms to get us. So we're this year well below average. What I want you to do is go to this site, and again, it's spelled out in the assignments on Canvas, and just click on the current year and the wet year and the dry year, and kind of see where we are and how variable things can be. And that's one of our big challenges in California is that, the difference between the wet year and a dry year can be huge. And we're okay if we have a dry year or two because of our reservoir system. But when we have 3 or 4 dry years in a row, we start to have problems because our reservoirs just aren't designed to hold that much water. So I hope this was helpful, and please email me, and we'll be in touch.